Hello and welcome to video number 3 on alkynes, some of our really newer material now. I won't emphasize too much about nomenclature. Check that out in section 9.1. You should be able to name simple alkynes, and there's some on your own problems on that. Alkynes have similar reactivity to alkenes, so that harkens back to last quarter, end of last quarter. And the reactivity of these kinds of molecules is based on the arrangement of their pi electrons. So an alkene has a pair of pi electrons here. An alkyne has two sets of pi electrons. If we draw pictures of that, we have the alkene here below, and the pi electrons of the alkene typically would react in this manner in bond-forming reactions. Of course, that also entails this bond breaking and leaving a plus charge behind at one of the two carbons. So you can visualize it as sort of a door swinging open in one direction or the other. Sometimes there's a preference for which way it goes. An alkyne has a pi bond also in front and back as well as above and below. So there's a second set of pi electrons like that. But the reactivity is basically the same in bond-forming reactions. Now, if you remember, alkenes can be brominated. The reaction goes trans, meaning they attach on opposite sides of the molecule. And so an alkyne can similarly react in that way, generating a brominated compound, but the double bond is still left behind. We went from triple to double. So this can actually continue assuming there's enough bromine to react, giving you a pretty heavily brominated product. And the reason it goes trans, you'd have to refer back to the mechanisms shown in the book. So we won't go into that right now. Incidentally, all of these would be methyls, technically, if I didn't draw these squiggly lines here, but I'm just leaving those out for clarity. I have them here on the side, on the left side, initially. Okay, so continuing with reactivity of alkenes, to recall, we have these alkene pi electrons. They can pick up a proton, kick off this chlorine, you get your new bonds. The chlorine comes back in a second step. You can review that chemistry that we did before. So an alkyne can react in a similar way, generating initially a chlorinated product. But then you still have this double bond, so this can actually repeat as well. And what you're going to end up with is a second hydrogen adding, and now you have two chlorines here. And so it just keeps going like that, unless there was some possibility of stopping it, like maybe if you only added 1 molar equivalent of HCl, if that was possible. Seems likely that it's possible, but hard to control. Another reaction we learned last quarter, at the end of last quarter, was reduction of an alkene, in this case, using hydrogen gas over a metal like palladium or platinum. So you can check out the figure, I think it was figure 8.5, I want to say, in chapter 8, that shows how this takes place on the surface of the metal. You get cis hydrogenation, a reduction reaction. Notice the double bond is gone. An alkyne can react similarly with hydrogen gas over platinum or palladium, and you would get at first addition of a pair of hydrogens like that, but then it's really not possible to stop this because you certainly can't really regulate gases very well. So you would inevitably end up with a second hydrogen adding, cis again, and so you have complete saturation of the molecule with hydrogens. So it's of interest that if you didn't want this, to be able to stop it at this point. And so there is a way to do that. To reduce only to the alkene, you add what's called Lindlar's catalyst. And basically, this is a metal catalyst as well, but the metal has been deactivated significantly so that it's less active. And then the hydrogens add, but then it just stops there because of the lower activity of the catalyst. The book has details of what Lindlar's catalyst is, but the essential thing here is that you have a choice, that you can stop at the alkene or go all the way to the alkane, fully reduced. Finally, another key piece of chemistry here, probably the most important part, because it gets us into more organic synthesis concepts, is that the terminal proton of an alkyne, like this one here, is acidic, meaning removable by base. It takes a pretty strong base, so a hydroxide, like sodium hydroxide base, is not strong enough to remove this hydrogen. But sodium amide, which is strangely named, is strong enough to remove this hydrogen. The electron arrow pushing for that would be a bond forming here, and this bond breaking here, depositing those two electrons onto the terminal carbon of the alkyne. This is now a carbanion. And you see throughout how important formal charge is. This sodium amide would be drawn like that in Gen Chem, and so you wouldn't really have the understanding that it's ionic, or even if you did, that these electrons are reactive in this way. So, but that opens the door to another rant, and I'll stop that right there. So we have this very useful carbanion. Why is it useful? This carbanion is useful because you can form a bond from these electrons to the carbon of a primary alkyl halide. This carbon is partially positive because of the electronegativity of the bromine, which is partially negative. So this is polarized. You have electrons going from high electron density to low, kicking off these electrons toward the more electronegative bromine, which makes sense that they would want to go in that direction. That's a bond breaking reaction, so bond forming, but more importantly, it's a carbon-carbon bond that's forming. And since all organic molecules are basically carbon frameworks, a carbon-carbon bond forming reaction is really, really useful and important. This is bond breaking here. So you end up with a new bond, as you can see here, and an extension of the carbon chain. And now you can see that if you can do this, you can do this with anything attached here, anything attached here, anything attached here. You can mix and match. You've now learned 1,000 reactions if you understand what's going on here. One caveat, it has to be a primary alkyl halide, like I said. So that means that this carbon is connected to only one other carbon. Carbon 1 is connected to only one other carbon, a primary alkyl halide. If you put a bunch of these reactions together, you see that we have a multi-step process. This is just one example, but this is sort of where we're heading. You can remove that proton, make this acetylenic carbanion. That can react, displacing this bromine to form this new bond. Now you've extended the carbon chain. You could reduce it to this alkene. You could even react it further with HBr to get this, and check it out, you've got chirality. Okay, your assignments are below. I'm almost out of time.